Welcome. You can see here is a new problem at your screen, and let me read you the statement of the problem. And it says determine the rate of decrease u of the radius r of a soap bubble when being deflated via a tube of radius r that is less than the radius of the bubble. The tube volume is negligible compared to the bubble volume. The air inside the bubble can be regarded as being still, but it needs to move. The surface tension of the soap bubble is sigma. The air flowing out of the bubble can be considered as an ideal incompressible liquid of a density rho. That is an important information. And let's start solving the problem. We know the surface tension of the soap film produces an extra pressure inside the bubble, and this extra pressure will be simply written as delta P, and its value is 4 sigma by rho. Remember, this is a soap bubble. So or you can also say that the film has two surfaces. That is why this extra pressure should be twice of 2 sigma by r. And now let's focus on the work done by the soap film, and it will be equal to the kinetic energy of the air blowing out of the bubble from work energy theorem, because air is flowing out of the bubble, and so it will gain some kinetic energy, and it will have some velocity. I guess it will have some velocity inside the bubble, and I call it B, and mass of this air flowing out, I suppose delta m, and so the flowing out air has a kinetic energy, and that will be equal to the work done by the soap bubble. And work done by the soap bubble can be simply written in form of pressure and volume, as pressure is delta V, and change in volume is simply change of the bubble volume, basically, is delta V, if I can write it delta V. So this is the work done by the bubble, and it will be equal to change in kinetic energy of the air flowing out, and that I would like to write it half mv square. Simply delta m is the mass, and delta m is the mass of displaced air, and delta V is a bubble volume decrement, and therefore we can simply, if I can put delta m by delta V as the density of air, this is rho is the density of air, and that is given, and it should be treated like an ideal incompressible liquid, as mentioned in the problem. So rho is delta m by delta V, so I can write this statement, this one, simply as V equals, or I would like to write it as delta P equals half rho V square. That means I got the value of V simply as 2 delta P by rho, and this is going to be a statement for further use. So let's calculate the thing we needed to find out the rate at which the bubble volume decreases, and this will be simply dV upon dt, and V can be written as 4 by 3 pi r cube. R is the radius of the soap bubble, and its value dV, this rate of decrease of bubble volume will be equal to the volume, the rate at which outcoming liquid through this cylinder or something, tube, outgoing rate of outgoing liquid through this tube. And if I know its radius that is given, so its surface area becomes pi r square, and its radius is small r, so we can write its surface area as pi r square. And if we multiply this by this thing volume, the velocity of the outgoing liquid, this is some kind of liquid, so that I can write here dV by dt will be equal to V multiplied by pi r square, the area. The cross-sectional area of the tube is pi r square, and you need to, and now you know what to do to calculate dV by dt. You can simply write here 4 by 3 pi multiplied by 3 r square dr upon dt. So the left hand side is simply 4 pi r square dr by dt, and the right hand side V, the value of V is 2 delta P by rho, and delta P is 4 sigma by r. So I can write here this V thing will become 8 sigma by rho r, and multiplied by pi r square. And now we can find the south value of U, and that was equal to dr by dt. After calculation, you will get something like r square by r raised to pi by 2 under root rho by 2 rho, and the problem is solved. Thank you for watching.